Hi class, welcome back to the lectures on quantum field theory, and this is chapter 2 on Lagrangian field theory and the first lecture on this chapter. Please take note of the books that you can read along with this lecture by Kakush, Mandel and Shaw, and Gross. So in this chapter, we'll be studying about Lagrangian and Lagrangian densities. So the theory of quantum field, the study of the quantum field theory begins with functions known as the Lagrangian. So a system has a Lagrangian, and this is constructed by taking the difference of the kinetic and potential energies. And in classical mechanics, these are used in deriving the equations of motions of moving objects. These methods are applied to quantum field theory as well, and the same techniques actually are being used to derive field equations. So first we'll go to the basic Lagrangian mechanics that we've studied in classical mechanics. So for simplicity, we'll take just one dimension, take one spatial dimension, say x, and we consider just the motion of a single particle. So T is denotes the kinetic energy of the particle, and V is denoting the potential energy of the particle. And the Lagrangian is defined as T minus V. The Lagrangian is a fundamental concept which captures all the dynamics of a system and allows the determination of many useful properties like say averages, dynamic behavior of the system. So those are basically what is the Lagrangian is gonna be helpful to our study. So given the Lagrangian, the equations of motion can be found through the Euler-Lagrange equation. So for a single particle moving in one dimension, the Euler-Lagrange equation is given by this. By the way, the dot here denotes derivative with respect to time. So this is just this one. Now, we'll consider a particle of mass m with kinetic energy T equals 1/2 mx dot square, moving in one dimension with a potential with a constraint and a potential v of x. So we'll use the Euler-Lagrange equations to find the equation of motion. By the way, the potential here is not specified. So we follow 5 basic steps in doing or in looking for the equation of motion. First, write down the Lagrangian. The second is that we're going to get the derivatives with respect to x, and again also take the derivatives with respect to time, and then derivative with respect to derivative with respect to x dot, then derivative with respect to x, and then we'll form the equation. That's just the basic steps in looking for or in finding the equation of motion of system. So again, we'll consider an example. A particle of mass m with kinetic energy T is equal to 1/2 mx dot. Where the kinetic energy is equal to 1/2 m times x dot square. And this is moving in one dimension with a potential Vx. Here, the potential is not a function of x dot, only x, only the space. So we'll use the Euler-Lagrange equations to find the equation of motion of this particle with mass m. So we follow the 5 basic steps. One is to write down the Lagrangian, then calculate the derivatives, and then of course we'll form the Euler-Lagrange equation to get the equations of motion. So for this Lagrangian, the derivative with respect to x is just mx dot, because you don't have an x dot here. And the partial derivative with respect to x is equal to just minus partial of v with respect to x. Of course, this term here does not contain space, only velocities. So if we do it, then we will be able to find this one, as we have shown earlier, and then the time derivative of this is just equal to mx double dot. Here you have m dot is equal to 0. So by the way, this is a kind of force. We knew earlier in the basic physics that force is just mass times acceleration. So if you, this is also shown earlier, and then finally you have the Euler-Lagrange equation here, which is equal to 0. And now we have, from here we have this one. What can we say with this? If the force is conservative, by the way, your potential can be derived by integrating the force. So anyway, the force is just the differential of differential of the potential, or the del of the potential, and in one dimension you have this one. So therefore you have this and this one. So if the potential is conservative, you have F is equal to ma. By the way, this is what we know in basic physics. Example number 2. So by the way, the equation of motion is this one. It's the equation of motion. So example number 2, Consider a particle of mass m undergoing a simple harmonic motion. The force on the particle is given by Hooke's law, which is F of x equal to negative kx. Determine the equation of motion by using the Euler-Lagrange equation. So again, here your kinetic energy is given by T equals 1/2 m dot mx dot square, and you get the potential by using this force. So F is just equal to negative V partial of x. If F is just a function of x, then this would be just V integral of F dx. So when you integrate negative kx, it's just 1/2 kx squared. So your Lagrangian is looking like this. This is the kinetic, and this is the potential. I'm sorry, this is supposed to be negative f integral of f dx, so that when you integrate this from 0 to x, you will get v to be equal to this one. Now you will have to get the derivative of L with respect to x dot, and this is just once again m x dot, and the time derivative would just be mx double dot, which is a force. And then when you derive L with respect to x, you will get kx, and again this is the force, the original force given. So therefore, since this is equal to this one here, you will have the equation of motion to be this one, the equation of a simple harmonic oscillator. And this could be written in terms of the natural frequency omega sub O square, which is just equal to k over m. K here is the spring's constant. For the case of an object attached to a spring that follows the Hooke's law. So those are classical Lagrangian, and we actually apply these things to get the equations of motion of fields instead of just objects or a particle. So an important quantity that we deal with in particle physics is the action, and it's denoted by L, and the definition of action is just the integral of the Lagrangian in classical mechanics. So the action is a functional, as it takes a function as an argument and returns a number. Particles, you should remember this, that particles always follow a path of least action. So we will minimize the variance of the action, and because the path actually followed by a particle can be determined, uh, if we um, minimize the variance of the action. So considering two fixed points, x1 or I mean xt1 and xt2, this is the position in the initial time and in a later time, t2. There are an infinite number of curves connecting these points. This means that there are an infinite paths for the particle to follow between these 2 points. But the actual path of the particle is the path of least action. Or this is the path, or the path of least action is the minimum, represents the minimum, extremum but minimum. So to find this, we set our action to like to make variance. So here your action, and this is now a disturb or perturb action. But the perturbation here is, we should show that, or we should set to be we should set to be equal to 0. I'm sorry for this, but this is supposed to be, it's supposed to be S plus Kronecker delta, or no, not the Kronecker delta, but a delta S, the change in the action, not a differential here. It's sorry for that mistake. As well as this one here. So this is supposed to be delta S. So I had to go back to this slide. By the way, the path followed by the particle is the one for which the change in action should be equal to 0. Here, this is supposed to be delta S. As here it's written as differential of S, but it's actually delta S. So computing the variation of the path leads to the equation of motions for the system, and we will find out that this is just the Euler-Lagrange equation. So basically, we go back to classical mechanics and start with the derivation of the second law of Newton. So we consider a small change in coordinates given by this one as a start. And the epsilon here is very small. And this version is constrained to keep the endpoints fixed, such that we are able to get the minimum path delta S equal to 0. So at initial time, the epsilon should be epsilon t1 should be 0, and at the final time epsilon of t2 should be 0. So we can expand the potential by writing it in Taylor series expansion. So if you have a small perturbation in your coordinates, say epsilon, and then you can write this function as in terms of this. Actually, there's a term, it's supposed to be epsilon square over 2 factorial plus d v dx, and this is already very small, and even much smaller is the epsilon cube, and so on. So we neglect those terms and just consider these terms. So the action becomes this one here, and this is supposed to have a bracket. So when you perturb x, your x dot would also be perturbed. So your x dot will be replaced by x dot plus epsilon dot and square that, and then your vx here would have to be written this way. So we'll expand this one here is x dot plus epsilon dot square is just equal to this. And of course we neglect this term, so that we're just going to consider this term to be replaced to replace x dot plus epsilon dot square. So now we have our action to be written this way. And the terms containing epsilon must be isolated. We should isolate that, because later on we will have to set that to 0. We will use integration by parts to this term, so that we can rewrite our action to be this one here. But anyway, we're just doing the integration by parts. So this is just a formula for integrating by parts. So here we use the fact that at the end points the variation vanishes, to preserve the end points, the initial and final points of the system. So this one here will be set to 0. Not really set, but it's really equal to 0. So your first integral will be simplified to this one, and of course this is equal to this one. Now collecting the terms with epsilon, so we will have this term and this one here, so that we can rewrite the action to be this one, but this one is just the action, and this one would have to be your delta S, and we require that delta S is to be equal to 0. So we're able to derive the second law of motion of a particle in classical mechanics. This one. So if we consider a more general situation where there are n particles or n number of systems or n generalized coordinates qit, where I is equal to 1 to n, so the Lagrangian would have to be expressed in terms of the coordinates and their first derivatives. So anyway, this is the action. This is the action, and then the system evolves from an initial point q1. This is just a time t1, and q2, which is the final time, which is the coordinate at final time t2. So again, I made a mistake here. This is supposed to be delta s. The trajectory followed by the system can be found by applying the principle of least action, and so delta s is equal to 0. So again, we have to set the endpoints to be equal to 0. I mean the so this is actually, I'm sorry for this delta q t1 equal to delta q t2, which is equal to 0. So this is just I mean a fundamental theorem in calculus where the change of a coordinate system and its derivative with respect to time is, you can interchange it. So with this, you have the change in the action is just the change of this integral. So you will have to write L. This is a function of qi and qi dot, so it should look like this. The total differential of L, because it's a function of two variables. So anyway, this is as pointed out here. You can write this term as this one. So again, we now use integration by parts of the second term by transferring the derivative to what we have to do is to eliminate this double derivative here, dt and of the change delta, so that our integral would have to be looking like this. So if we factor out this one, and write it outside qi, this is just the Euler Lagrange equation. And since qi, change of qi is arbitrary, meaning it can have any value, including 0, of course. And since we require this is equal to 0, but this is not equal to 0 all the time, so that your your equation here should be equal to 0, and this one is just qi. Again, I'm sorry for that. So therefore, the principle of least action gives rise to the Euler-Lagrange equation. And also, in this particular result, the Lagrangian satisfies the Euler-Lagrange equation independently for each coordinate. Looking back at examples 2.1, 2.2, the derivative of the kinetic energy with respect to velocity was the momentum. And this is a completely classical result. So it is much more common to work with, more convenient to work with canonical momentum. This is more general and useful, and we define the canonical momentum to be equal to the derivative of L with respect to qi dot. And now we define the Hamiltonian function in terms of the Lagrangian and the canonical momentum. So here is the Hamiltonian function. We will be discussing these things in more detail in the following chapters. So we'll now go to studying the fields, and we will use the techniques used in classical mechanics to find the equations of the equations of motion of the fields. So we are now dealing with fields, and this is a function of space-time. Or we can write this more compactly as this one. The x there could be time or space, time and space. So in a continuous case, we actually work with the Lagrangian density here instead of L. So the action now is written in this way. The integral of the Lagrangian density with respect to four coordinates, time and space, with respect to space-time. So the Lagrangians depend only on the fields and the first derivative, that is this one here. And the fields of interest are local, meaning that a given space-time point, the Lagrangian density depends on the fields and their first derivative evaluated at that point. Now we're going to apply principle of least action. So again, we vary the action with respect to the field phi x and with respect to the first derivative in here you have to use partial mu, since you're now dealing with space-time or coordinate system. So our action, I mean the change of the action should be equal to 0, and then this action is just equal to this one here, and or you can say that that is also written like that. And then since this L is a function of the field phi and also of the derivative of phi, then the change could be written by this. This is of course equal to 0. So if we apply the integration by parts to the second term and use the fact that these are equal, boundary terms vanish since the endpoints are fixed, and the second term becomes this one here. And so the variation will lead, the variation will lead us to this expression, but then again our change in the field is arbitrary, of course including 0, but in general, if you have an integral that is equal to 0, then this must also be the whole thing here must also be 0. So may I just read, the integral is again 0, and there are two cases. Either there is cancellation because of the integrand, because the integrand takes positive and negative values, or the integrand is 0 over the entire domain of integration. So but it's the cancellation, I mean, of the integrand is not really all the time possible, because we have a change in the field phi, which is arbitrary. So in this case, the domain of integration can vary, so cancellation cannot be relied upon, and the integrand must be 0. The term inside the braces must vanish. And this is just the Euler-Lagrange equation for the field phi. Here. And when you, as we have discussed in the previous chapter, when you see an index appearing twice, that's the sum. That's just the sum. So here we have this one. So this means that it's a sum. Not really the sum. I mean, it's the expansion when you see an index being repeated twice. Because the Einstein sum would have to be a covariant and a contravariant. That's the sum, actually. I'm sorry for my mistake earlier. So this is what it is. So if you see a repetition of index, then it would mean this one here. So the canonical momentum density for the given field would have to be this as a counterpart of the classical canonical momentum. And so the Hamiltonian density of the and the Hamiltonian would have to be written this way and that. So now let's find the equation of motion and the Hamiltonian corresponding to the Lagrangian, this one here. So the Lagrangian is 1/2 partial mu phi square of that minus m square phi square. So again, we can do a straightforward application of the Euler-Lagrange equations for fields, and then we treat here this one as a variable, an analogy to x dot in classical Lagrangian, and then we think of our phi as x, and then you can think of this as another variable, so that when you do this, that would be equal to 0. Now we compute this one here. So let's begin by expanding the first term of the Lagrangian, this one. This is actually what we discussed in the first chapter. And we can use the metric to put the index down of this term here, so that we can get the derivative. So let's take a look. So first, here we have partial differential with respect to partial mu phi, and this is 1/2, and we can write this down as this one here, and then of course this is equal to 0. I mean, it's here. So let's take a look at the first term here, this one. Now we have this one. So if we get the derivative, so this is just g mu nu partial nu phi plus and then we get the derivative of this with respect to this one here. So we have this, you can put this ahead of this term. So this one and this one is left, because the derivative of partial nu phi with respect to partial mu phi, this is just equal to the Kronecker delta nu. So if they're equal, then it will be 1, but if they're not, it it's 0. So therefore this is just equal to 2 mu, 2 partial mu of phi. So finally we have these terms. And this one. And so we can now get the equation of motion, which is equal to partial mu phi plus m square phi is equal to 0. This is just the Klein-Gordon equation. The Klein-Gordon equation. Or you can actually just write this as mu phi plus m square phi is equal to 0. By the way, partial mu is equal to this. So you have this one here, and that is just the Klein-Gordon equation. Now we will derive the sine-Gordon equation as an example. So we have here the sine-Gordon equation. This looks like the Klein-Gordon equation. So take the Lagrangian to be this, and again first calculate the derivative of the Lagrangian density with respect to phi. And so this one is this one would have to be 0, and the derivative with respect to phi would have to be 0. So you only have 1 here. So this is just negative sine phi. The Lagrangian only has one spatial coordinate, so we have in this case only one coordinate for the space. Now taking the time and space derivative separately leads to this one and this one. And so combining all the terms all together, we will be able to find the sine-Gordon equation. You can also solve this at your own pace, resolve the problem, so that you will also learn how to do the things. So if by the way, this is the end for the last slide for this lecture. I hope you have learned something for this session. Symmetries and conservation laws would have to take a lot of time, so we will just postpone the discussion to the next lecture on this chapter. So I hope you learned something and maybe you can ask questions later on.